So it looks like we are all, so it's good. So I'm very happy that we made it up to the end because, you know, you never, as you test always, you never know how this will be. And, you know, so I think it's good to have the last lecture and say we are here, and that means we can finish. So very good. And also thanks for coming because I know it's difficult. You always have to test and so on. So I think lots of difficulties. Are there any questions to Monday or before? Everything is clear, so it's good. So it's, I envy you in a sense. So I want to tell you something about how to, I mean, today it will be more like that I tell you some technologies, how to deal with problems that maybe are not such that the integrand, depending on the gradient, is quasi-convex or polyconvex or so. So because there are problems like that. So we have seen this one-dimensional non-convex problem, but in the high dimensions you can have the same. And there are even like material models where the energy cannot be polyconvex. These are these famous shape memory alloys, and I think you have already seen many experiments like that the material changes this shape if you put it to water, the hot water, and you know you deform it, then you put it to the hot water, and it goes back to in shape. So these materials have typical kind of energies which are not polyconvex, not quasi-convex, even not rank 1 convex. So you have to do something to if you want to solve the problem. So the minimization problem. Of course, what you can do, and people started to do it in early 90s, say that they simply did the finite element discretization and calculated something. And this just means you may approximate the infimum, but because there is no minimizer, it's difficult to say what you are really approximating. So this is more like that you approximate the energy than just any minimizer. So the question, how do we converge, is complete nonsense because there is no solution. So but you know, in the beginning you try everything to get some idea and so on. So, but if you have I mean, we will today assume that we have our function w, which will maybe be bounded like some constant, and then we take this will be my w of f, and this is bounded above by another constant. So this is another constant, so maybe I put tilde here, 1 plus f to the power p. P is bigger than 1 to avoid problems with non-reflexivity and so on, and C and C tilde are positive, and then we work on matrices. So F belongs to M times D, and this is supposed to hold for every F, and the constants are independent of F. So these are like coercivity and gross conditions. And when we assume the W is continuous, yeah. So now that's just inspiration from convex analysis. When if you have a function, you can calculate its convex envelope, that you take all affine functions or convex functions below it. So now you can play the same game with the other notions of convexity. So we define WQC, and this is the supremum of all functions V, which are in the same phase V is quasi-convex, and V is below my W. And I end the definition. It's a pointwise supremum. So you say my WQC at the point A is a supremum of VA such that V has these global properties. Is there any? So we needed to show that there is some quasi-convex function below my function, because if there is nothing, then the supremum of the empty set is minus infinity. No? But there is one, because you have the bound. So that's convex even. So that's good. So that's why I put this this bound here. And you can also do it for other notions of convexity. You can say rank one, and this WQC is called quasi-convex envelope of my function. The quasi-convex of W. And in the same spirit, you can define other notions of envelopes. So you take polyconvexity, and then you get a polyconvex envelope. And then you take rank 1 convexity, and then you get rank 1 convex envelope. And then you can also take convexity if you want, and then you get a convex envelope. The trouble is that that's very implicit definition. Like what, how can we estimate the envelope if we have just this definition? So we know, for example, now that maybe I can estimate it from below by this function, but it's maybe very rough. So it doesn't tell me much. So we need a better definition. And the better definition is the following. So we can calculate WQC at a point F as the infimum over every function phi, which is in W1 infinity 0 omega to Rm of the integral. Maybe let me put here measure of omega times WQC, and then I have the integral over omega W f plus gradient of dx dx. So this is the idea that this looks a little bit better. At least I can, if I have a point F, I can evaluate at least this looks like something more practical than this other definition. And it looks like it's a good definition, because if you look at the right-hand side, this reminds you the definition of quasi-convexity. But now we have to show that the notions are the same. So this is the claim. And then to prove it, we will first say that maybe we call this one here Q of W at F. and it's another function. And we have to compare these two. And the comparison is, and then maybe we say that this animal is the same like this animal. And so the comparison is like this. So first of all, what we say is that if I have this guy here, so first observation is that, so the first observation is that WQC is smaller or equal than W, because it's a supremum of all particles below, so it cannot be bigger. And this also tells me that if you look at this object, QW, then the QW is bigger or equal than QW QC. Because if I have a smaller function and I evaluate this integral, then I always get a small number. So this is and this is WQC. This is WQC because we say WQC at a given point F is the infimum over pi in W1 infinity with the zero boundary condition omega times Rm. Now I take 1 over a measure of omega, so the D measure, so the measure is always in R. The Lebesgue measure. And now I do the integrand. And here I put WQC, F plus grad phi of x dx. And this is the quasi-convex function. So this is bigger, and here there is the integral over omega, and this is bigger or equal than WQC at F times, no, I don't have to do the division because it's already here. So, so it looks like that this guy is bigger than this one. But this, you take phi equals 0, you get exactly this. So this is the same. So now we have to prove the opposite inequality. So we must show that the opposite inequality holds, so that WQC is bigger or equal than Q of W. For that, it would be enough to show that this animal here is quasi-convex. Because if you take, this is the supremum of all quasi-convex functions which are W, which are smaller than W. So if this is quasi-convex, then I would know it's there. So what we need to show that this is satisfied. So the WQC is bigger or equal than QW. So in we must show that this is quasi-convex. So we must show that one divided by the measure of omega, and then here QW of F plus gradient psi. Now I use psi, I tell you why I use psi. Dx is bigger or equal than Q of W at F. And it would be enough to prove it for every psi which is in W1 infinity, but piecewise affine. Because these functions with zero boundary condition, because these functions are dense in W1 infinity in the by the approximation in the LP norm, say. So what you can say is that the following. So you want to so for every psi which is W1 infinity, 0 omega m and psi is piecewise affine. And it means finitely many pieces. Psi is piecewise affine and has finitely many pieces. Yeah, so now we test with only piecewise affine functions. And so, because this is W1 infinity, 0. So we just want to prove this, because I mean the quasi-convexity would be that you here have a general function, so it also has to hold for a smaller class. Yeah. Is it on? Yeah, no problem. So yeah. So now we take we want to take the infimum over the left-hand side, and we want to show that this is bigger or equal than Q of W of F. So because if I take the infimum, then I would know that I can take some representative from here, such that if I add a bit here, then already the left-hand side will be below that from the definition of the infimum. So we take so psi is piecewise constant. So we take, let omega I be a subset of omega such that psi, the one which we have here, is affine on omega I. So once you have this omega here, you divide it into many pieces, and then omega I will be one piece here where my function is affine, so the gradient is constant there. And so now I take the definition of Q of W at this point, and so then I know that there exists phi I, which is in W1 infinity 0 of this omega I of this little piece. So this was the whole omega 2Rm such that now if we calculate the following, we calculate the Q of W at F plus grad psi. So this is bigger or equal than 1 over measure of omega I, d-dimensional always, of W F plus grad psi plus grad phi E x dx, and I have to subtract some epsilon, such that for a given epsilon positive, this holds. So now I don't put any argument because here on this omega I, this is a constant thing. So this is a constant matrix. I could put here C if you want or something, but I mean, and this is the definition of infimum, because now we work on this little subdomain. So I find some from the definition of the infimum of my QW that there exists phi E if you give me an epsilon such that this is more than the, if I subtract epsilon, then I get above this. So this is, this has to be like this. And now you take this phi I, you extend it by 0 to the whole omega. You can do it because there is a 0 boundary condition. And you define phi, and this will be my psi plus sum over I. So these are the pieces here. And then you just do here this phi I. And this is in W1 infinity of the whole domain. And then these guys are these extensions by 0. To the whole omega. So effectively, you have it for, because this is finitely many pieces of this partition is finite. So I have it, the finite sum, and I extend this by 0 everywhere. So on every piece, I only have 1. No? So it's like a partition of the domain. So now you plug it in here. And now you plug it in, and then you get that the integral over omega QW F plus grad psi x dx is bigger or equal. Now I use the right hand side here. So it's a sum of all these. So you sum 1 over measure d of omega I gradient phi E x dx minus epsilon, and this is nothing else. Let me continue here. Then the integral over omega W, or the W is missing here. W is missing here. Me minus epsilon, and this is so finally I have this, and then this is F plus grad P, and I'm sorry, I think I don't have, yeah, here I have this, but now if I plug in phi, then this is already included, this piece. So I forget this, and I write this one here. X minus epsilon times the measure of you mean here? Yeah, there should be yeah, also times the measure. Thank you, Katharina. This was good. Yeah. It becomes the sum over I here, because here I have, this is piecewise affine on every, so it's a, so this is a, so psi is piecewise affine, so this animal is constant on each omega I. So this is like a fixed matrix, and this one is moving. But because this extension, I have something which is finally Lipschitz with zero boundary conditions on the omega I. And this gives me that this is bigger or equal than QW of F times the, I think I also should put here 1 over measure. And maybe this also applies to here. And this is bigger or equal than this one minus epsilon. So this shows, if you look at the left piece and the right piece, because epsilon was arbitrary, then we have that psi of x dx is bigger or equal than the measure for every psi which is W1 infinity with zero boundary conditions, omega Rm, and psi is piecewise affine. And that is integral over omega. So now from this we could already infer that this is a rank 1 convex function. And it means it's continuous. And then we can extend this to every psi, I mean general psi in W1 infinity 0. And this would tell us that this is quasi-convex. So this implies that QW is rank 1 convex by this partition and using rank 1 matrices is rank 1 convex. This means continuous. And then it tells us that this is, in fact, this is, and this implies that QW is quasi-convex. So it's a quasi-convex function which lives, which is below my W, and so I get the, but we have to show, we must show that, so it's a quasi-convex function which is below my function W, and so it has to be small or equal than Q, the quasi-convex envelope. Because if you have a function which is quasi-convex and it's below your function, then it's also below the quasi-convex envelope. Not strictly, but it's there. So now you have a formula for that. You mean this one? This is the first one. I think there shouldn't be. I think there is C missing. Yeah. So this just is just the definition. So this is the definition, the first equality. Yeah, because this was my definition of this QW. So given a function, you calculate QW like the infimum of. You mean here? Oh, now I'm a little bit confused. It's just the definition because we did not divide the measure. Aha. So the measure has to be, yeah. Thank you. So here we say that this is, you mean I should divide by the measure here? This was your omega. Yeah, so this is included here. Oh, thank you. Yeah, so the measure is here. And we kill it from here. So we can also, the simplest way would be to take omega in such a way that it has a measure 1. And because in fact this definition doesn't depend on omega. This is the same story like the definition of quasi-convexity doesn't depend on the domain if it's a Lipschitz domain. So maybe the best way would be to take something which has a unit measure. And so this is WQC at F because this is supposed to be, this is a quasi-convex envelope. So it's a quasi. This is small in W, but it's quasi-convex. So then this comes from the definition of quasi-convexity. So now I mean what we can do with this envelope also. So somehow we have problems which do not have any solution, but still you only have the infimum, say, and you want to still do something. So there is a technology which is called relaxation. You can relax in various ways. For example, lay on the sofa, but that's the difference. So it's relaxation in the calculus of variations. And it looks like the following. So we have it's a general technology. So we have our functional I, which is maybe defined on some set A, and this is a subset of some Sobolev space. That's Rm to R. And I mean, I don't put plus infinity here because it's a little difficult. It's not really clear how to do it in this case. But let's take that I takes only finite values, and perhaps this functional doesn't have a minimizer because we cannot prove it. I mean, we know that there are situations where the minimizer does not exist. So we try to find another functional you know what? Maybe forget here this Sobolev space. Let's do it really very general. So there is some set A of some, say, subset of some Banach space, if you want. Maybe we forget this here. We try to find another functional. So it goes from A to R. We try to find another functional I bar, which goes from A bar to R. Such that the following conditions are satisfied. So first, the infimum over A of I is the same like the minimum of I bar over A bar. So this already means that I assume that the new one has a minimizer, because I say it's a minimum. So in particular, I bar has a minimizer on A bar. So we try to find another function. So the focus of our search is the functional and also the set. So because the set A bar, maybe it looks like a closure, but it's not a closure. Not the closure of I. So this would be, I mean, then you can find plenty of functionals that satisfy this. So it wouldn't be too difficult. But there is another condition. It says that if UK is subset of A and I of UK converge to the infimum of I on A, then UK converges, and now the converge, so maybe I write converges up to a subsequence to a minimizer of I bar on A bar. And then the converges, this, I mean, I just write converges because I don't want to write any arrow, because the topology has to be, this is also a part of the game. What topology we use. So this is already a bit difficult because you have one that was easy. Here you have to show that, I mean, if you have an infimizer, so now, because maybe the minimum doesn't exist, so we have just some sequence which goes to the infimum, and this sequence contains a subsequence which in some sense converges to a minimizer of the new functional on the new set. And the condition, last condition, says that there are no more minimizers of I bar in A bar than, in a sense, minimizing sequences of the original. So if you have a minimizer here, then this minimizer can be reached in this convergence by some infimizing sequence. So there are no extra minima which wouldn't be in the original problem. If U bar in A bar is a minimizer of I bar on A bar, then there exists, so we had UK, so let me say we have UK tilde in A, such that UK tilde converges to U bar, and I of UK tilde converges to the infimum of I on A. Huh? And that's it. And if I can find a function I bar like that, so the problem which is defined by I bar and A bar is called the relaxation of I, of the problem I and A. And then so for example, I is called the relaxed functional to I. I bar. Thank you. So I bar is called the relaxed functional. So this is this somehow, in various, I mean, this you can also find this in other settings, like this is very close to the notion of gamma convergence, where in gamma convergence, typically you have not one functional I here or here, but you have a sequence of functional. So this is even like more general. Here the functional is one, and then you converge. So so related to gamma convergence, say. If your original function is already nice that it has a minimizer, then you don't have to do anything, because you can just say, if I have nice Lauer semi-continuous functional, so I can prove the existence of minimizers, I say my relaxation is the original functional there, and so this is the best. You can do it in any dimension, so and it looks like a perfect thing, because if we can find it, we have a minimizer and we have these properties, but it also has some downsides. So let's have a look at something what we have done last Monday. No, last Monday. Monday last week. So maybe you remember we had a functional which looked like that. So it was a integral between 0 and 1, and then we had something like u prime to the power 2 of x minus 1 to the power 2 plus u squared of x dx. And the point was to minimize it, this functional on the set A, and the set A was u was in W1, 4, 0, 1, and I think we had that u at 0 is u at 1, and this is 0, and also I think I put also that the minus 1 is more or equal than u prime of x, and this is more equal than 1. And we showed that there is no minimum for this problem. Remember, this was this zigzag function. So you go, no, so the minimum doesn't exist. Minimum doesn't exist. We only have infimum, and this was 0. Remember, this was this function which was going up and down, up and down, up and down, down, with the slope 1 and minus 1, and it was kind of getting the oscillations were getting finer and finer. So now you see what's the problem here already, because this function here in the gradient in the u prime is non-convex. It's a problem which has two minima at 1 and minus 1, so it's a non-convex problem. So because quasi-convexity in one dimension is like convexity, so this is because of this. So my W, my one-dimensional W would be something like that. So it will be something which is 0 at minus 1, it's 0 at 1, and it looks like this. And at 0, it's 1. So this is W maybe let me put here F, and this will be also F, and this will be F squared minus 1 to the power 2. F is now one-dimensional, it's just a point. So this is non-convex, and there is no minimizer. So we can ask, what would be the relaxation for this problem? So the relaxation here would be the largest convex function, which is below my W. And so the largest convex function is the following. You go to 0, then you take 0 here, and then you continue. Because on this piece, this is convex. The non-convexity appears only here. So I replace it by, I cannot do anything else because here I'm 0, 0 here. So if I'm positive here, I would create non-convexity again. So then I take this red piece. The convex envelope of W, and because we are in one dimension, you can also think about supremum of all affine functions that are below my original function. And as you can see, I mean, if you go like that, so you search for a tangent tangent line, then you here, and this is the so it's the convex, and also the largest convex function which is below my original W. And then I mean, because now this function is 0 as 0, I can plug 0 here, and then I have 0. So this works. So in this case, so I bar, so sometimes this convex envelope is called W star star. That's the notation. It's a big conjugate, so you know it is this Fenchel transformation. I think people say Fenchel, but I think it was German, so it's Fenchel. And this is and if you do it twice, then you get this. And so I bar of u will be just the 0,1 integral of W star star of u prime of x dx, and then the remaining term is here, and dx. And my a bar will be just a. And so this is now this problem satisfies all these properties which we don't have anymore, but we used to have them. Of course, this is still a point of the proof. But what I want to say that suddenly the minimizing sequence for this is just 0. So you have a new problem, you have a new minimizing sequence, but you completely lost the information of the original problem. Because here we have 0. And here the sequence of so this was the sequence UK. So the sequence of gradients UK prime was doing this. It was 1 here, then it was -1 here, -1, 1. It was again 1 here, it was again -1, 1, and so on. So it was just oscillating on a scale maybe 1 over k. So this is 1 over k, this is 1 over k, and so on. So it was faster and faster. So the gradients were oscillating like that, but I don't have it in the new problem because I just say 0. So I forgot this, I lost this information. So the general result is the following. So there's a proposition. If say so we have our W as before. And P bigger than 1. And I is defined as a integral over omega W grad ux of I of u. And u belongs to A, and this is a set which is subset of the W1 piece, Sobolev space, and I assume that A is weakly closed. It means if I have a weakly converging sequence, then the weak limit is there. So this avoids the problem that my limit is somewhere out of my set and I cannot really. Then I would have to kind of find some weak closure of my my set A. Then I bar of u is nothing else than omega. And now you can write QW or WQC of plus UK dx. And A bar equals A. And the convergence is the weak one in W1P. So this is what we know. And you can imagine that it's of just limited usefulness, say, because how do we find this envelope? That's difficult. And I mean, for many functions, because we don't know if some function, particular example is a quasi-convex function, how can you calculate the envelope? That's just theoretical result, but doesn't help us really too much. So we have a new problem, and this is more like for theoretical considerations. And this problem, in principle, even if we know it, then the same effect can happen here. So like in this one-dimensional case, that you lose completely information about the pattern of your minimizing sequence. And is it cold? No. Is it cold here? No. Is it? Aha, because you have open window. So I'm here completely isolated. So the point is that we are losing information. So now we are picky and we ask, can we get a relaxation which would also tell us something about the pattern of the infimizing sequence? So we have a new problem, and also we learn something about the old problem. So that's that we want more than that. We want more than we have. And the answer is yes, we can. And the price to pay is that we leave the function setting, but we go to measures. Because if you cannot find a solution in Sobolev functions, in the set of Sobolev functions, you say, maybe I can extend the notion of solution and go to something more general, and this will be this problem with measures. And the technology which is behind it, and it was developed, in fact, in late 30s by L.C. Young for some problems in optimal control, but it was retaken in 80s by John Ball and Richard James, who were kind of interested in the modeling of shape memory materials, so problems where there's non-convexity appears, non-quasi-convexity appears in general. And so this was studied, and kind of there was a flourishing period of Young measures. So Young. So this was introduced by L.C. Young in 1937. And then many various generalizations came after. And so the idea is like we have it here on this example where you have the sequence of gradients which is oscillating between 1 and -1. So, and so on. This was UK. And the thickness here is 1 over K. So the weak limit is only 0. So this is not much information. So UK goes weakly to 0. So in L2, for example, if you want. And it doesn't carry much information. So for example, if I take a modulus, we already know that UK doesn't go to the modulus of 0. And that's the problem. Because I only know the average, and if you have the average, then you have no idea what's the distribution of your value. So -1000 and 1000 have the same average like -1 and 1. So the result of, or the statement of L.C. Young is the following. So, I mean, it was first defined for an infinity function. So we can do it. So the proposition. So let UK subset of L infinity omega Rm be a bounded sequence. Then there exists a non-relabeled, so it's non-relabeled subsequence and a family of our new word, parametrized. You will see finally that it will be not so difficult. Parameterized measures nu. So nu is this is a typical notation. So if you look at some book on this topic, then you find nu. And the parametrization, I take nu, and this will be the family. So the family means I take nu and I put x here. X will be living in omega. So given x in omega, or almost every x, you get a measure nu x, where nu sub x is a probability measure on Rm. So probability measure means it's the measure of the whole space is 1 and it's non-negative. So the nu x is a probability measure on Rm such that lim for k going to infinity of integral over omega f of uk x gx dx can be written as the integral over omega, integral over Rm, f s d nu x d nu x, you integrate with respect to x, you multiply by g of x dx. So you can take it like this. And this holds for every f which goes from Rm to R continuous. And for every g in L1 omega. So it's complicated, right? So what does that mean? So you have this family, so for given x, fix x, and then this is a probability measure. So here you integrate with respect to this probability measure the function f of s. So this bracket here gives you something what depends on x, because there is this x fixed. So this is also has some properties that this is measurable, because then you multiply this function of x by g of x, and you integrate with respect to the Lebesgue measure. So this is just not a general family, but this has an even better property, because this gives you, if you plug here the continuous function, some function which is measurable. So then this is called weakly star measurable, but I didn't want to make it even more complicated. So why this will be useful for us? Because this tells me that it's a bounded sequence here. So you can pick up a subsequence which converges weakly star in L infinity. But that's the same problem like with weak convergence. If I plug some nonlinear function, then the limit will not be the nonlinear function evaluated at the limit, weak limit. Here I can do something, because here f is very general, it's a continuous function, so it can be nonlinear, and then it tells me what's the limit. And I will need it because the problem of us is that we have, say, our function w of the gradient of uk, and we are looking at lim inf. So if I know that lim inf, what's lim inf, then I can, this will help me, because then here I have an object which will not be the w at the weak limit, but this is something what I'm searching, so I'm after this. If I don't have a lower semi-continuous function. So the hope is that this might help me if I plug in w and put, for example, g equal 1, then it tells me something. So let's have a look at this. So I know it's complicated. Yeah? I mean, in general, we know they exist. You can also, what does it tell you? I mean, so if you look at, if you fix x, and then you look at, say, then you look at the measure for fixed x, which is the measure is sitting in Rm. So if you take a subset of Rm and the measure, then it tells you some probability that the sequence will sort of accumulate close to it. So we will see it for, I will do some examples. But first I want to do the following. So if you take f of s, so we are now in Rm, so it has m components. So I take, this will be just s. So this is a vector valued function. So I take si and I do it. Fi will be si for every I. So I mean just the linear function. And you plug it here, and then you take g general. So what do we have? That the limb of, now we have UK x dx or g then this is now the integral over omega. Here I have f of s is s, so this is s d nu x s integral over Rm, and now I have gx dx. And my sequence has also a weak limit, say, weak star limit in L infinity, and this will be some u. So this u, so at the same time, this converges to something in omega ux gx dx. It's a weak star limit. It's u. So what you see here, that this is the u. The inner piece is the u. So so ux is the integral over Rm s d nu x s for almost every x in omega. So the weak limit, or weak star limit, if you want, is the first moment of the measure for a given x. So the first moment, or the mean value. So let's have a look at our sequence here. This is the typical situation. So this is bounded in infinity on one-dimensional space, has values 1 and -1. So if I say that the measure tells me what's the distribution of my or the values of the sequence in a given point, so if you fix a point and so you fix the point and you look for the sequence, and then it goes faster and faster, the scale goes to infinity. So it's up or down, it's +1, -1. You are just looking up and down, faster and faster. But you do it with the same probability. I mean, with the same frequency. I mean, the time you spend looking up is the same like time you spend looking down. So in a way, it's if I search for a probability measure, it's just half of the Dirac at 1 plus half of the Dirac at -1. So if the sequence is like this, I mean, so UK oscillates between 1 and -1, then on the scale 1/k, then nu x is half of the Dirac at -1 plus half of the Dirac at +1. And if you +1, and if you want to prove it, you simply plug it to this formula, and you see it works. So in this case, there is no x dependence of the measure, because the sequence, if you zoom in a particle, this always looks the same. If you go along the interval 0, 1 and you focus on a piece, then it's always the same. So in this case, it's called, so nu x doesn't depend on x, so it's called homogeneous measure. Young measure. And if you plug it to my problem, for the gradient here, then this is just the, if you plug here the measure here, then you see that really the evaluation of the integral is 0. So this is the right thing. So because it carries much more information. So the first moment of this measure is 0. It means the weak limit of my sequence is 0. Yeah, so this you can do. There is also another part of this result, which I didn't mention, that if you have some compact set in Rm, and there is you have probability measures which are supported on this set, and then you need this property that this family of measures has this property that it's weakly star measurable with respect to this x. Then you can find a sequence which satisfies this relationship. So this is good, but this is in L infinity only. So there are many problems which you still have to look at. So first of all, can we do it in LP if I only have a sequence which is bounded in LP? So here there will be P. I can do that, but then there is some price to pay. First of all, if this is LP and this is any continuous function, then it might be that it's not even, the integral wouldn't be finite. So you have to restrict your F. So the F, so the LP version. So the question is, how about if UK is only bounded in LP? Bounded, and one is with P, and this is really smaller than infinity. So the answer is the following: the formula star so then there exists a set of there exists nu, it's nu x. That's the same as before, but the formula star holds only for G in L infinity. So we go from L1 to L infinity to smaller space, and F, which is from Rm to R continuous, such that the limit for argument going to infinity f of s divided by s to the power p equals 0. So you have to take functions that at infinity have a growth smaller than the polynomial. And because now if in this case this is very close to L1, then this has to be only L infinity because of the Hilbert inequality. So this is something what we have to, so that's the result in ATs due to Maria Schoenbeck. I put it up. And there is a simple example. So look at the following. You take a sequence 0, there is 1 here, and there is maybe 2 or so. And you take a sequence, there will be UK, and the UK will be such that it will be 0 here, up to 1. Then I look at 1 plus 1 over k. And in this little interval, there will be 0 again. And in this little interval, this will be k to 1 over p. So if k goes to infinity, I get something thinner and longer. And then it's again 0 here. So this is a sequence which is bounded in a p. The integral is 1. So UK is bounded in a p. So we can subtract a subsequence, and the result says that there is a measure. So what do you guess? This is 1 plus 1 over k. Okay. Yeah. So the area here is just 1. So then the guess would be that, because if you look at the sequence and you look at this probability distribution, if you are at almost every x, that's 0. You know? So if this is 0, so the measure will be, you always look and then say there is a 0 only. So I say the probability measure which describes the sequence will be Dirac at 0. No? Is it believable? But then, if I plug my f of s equals s to the power p, if I would take the LP norm to the power p, then the star doesn't hold, because the star is 1, and then the right-hand side, if you evaluate this function at Dirac at 0, you get 0. So if then star doesn't hold, so left-hand side equals 1, but the right-hand side equals 0. Right-hand side. And so we really cannot do that. The point is that this sequence, the UK to the power p, is not equi-integrable. I cannot. This is just that we need some restriction of f, because I mean, this is still in L1, but the result doesn't hold. So because so we cannot take this f. So this is just to show that this f is not allowed. So we cannot really take this f. We could take this f if we know that this p power is equi-integrable. So that this sequence of functions is much nicer. It doesn't concentrate in the p power. Then we can do that, but not in general. Yeah, you mean here, you are right. So This is a vector, so I take m functions. Fi will be just the i's component, and you do it like that. So you do this is like a weak limit of a vector valued function, so you do it component by component. So this is a sort of simple notation. So now, okay, so you say maybe we can do something with this in our variational problems, but there are a couple of difficult points. So first of all, typically if you have W with some growth, some polynomial growth, your sequence is bounded in LP, or the sequence of gradients is bounded in LP, and the P comes from the growth of your function W. But at the same time, you want to calculate the limit for W which has the same growth. So this is the typical situation where the growth is exactly as the bound on the gradients. And this example shows that we cannot do this, because then we can get something wrong. So that's one thing. And the second thing is that here I have gradients. And maybe I can, so the question is, if I have special functions like gradients, does it give some condition on this Yak measure in the limit? Or can it be any collection of probability measures which has this measurability property? And that we have to answer. So maybe I erase a bit. Uh-huh. Ah, yeah. So here, I mean, this is defined for almost every x, because you just use the Lebesgue integration. So this is new x. I mean, so you can forget the 1 at 0. So you forget 1, you can define it as you want. And the rest is Dirac at 0. So it's again independent of x. Because, I mean, if you look at your sequence, then you sit somewhere a part of precisely 1. You sit somewhere here, maybe here. Then for some k, you already see 0, because this gets thinner and thinner. And then for the rest, from this k, 0, you only are at 0. So you only see 0. And only one point in the limit is different from 0. It's like Dirac at infinity. But then this point we can forget, because it's for almost every x. You can also have if you have a sequence which is maybe 0 here, and then you start to do these oscillations between 1 and -1 only here from some point x0, and then you oscillate between -1 and 1, and then the sequence will be 0 here. Then you get a non-homogeneous measure which will be nu of x, if this is 0, is Dirac at 0 if x is in 0x0, and then it will be half of the Dirac at 1 plus half of the Dirac at -1 if x is bigger than x0. So this is not homogeneous anymore. Because if the sequence is such that it's 0 here and then it starts to oscillate, then the measure will see that also. So this was because up to now we had only homogeneous measures, and so you mean for the example here? I mean, for x equal 1. Because I mean, you can change it in one in say 0 measure set, but not everywhere. But I mean, if you want, we can say that nu1 is Dirac at or whatever. I mean, arbitrary. Sometimes it's difficult. I mean, if you have a sequence in vectorial space or your matrix space, then to calculate a measure is difficult. But the result is there exists a measure. And so if you have a sequence which strongly converges, then it also converges weakly. So the question is, can we get a measure for this sequence? If UK converges strongly to some U in LP, then nu x equals Dirac, but now where? At the point U of x. So now this is really non-homogeneous. So this is, you take x and then you say this is the value at U of x. Because, I mean, it means already, and this is very good because it tells you that you are with high probability at the point U of x, because it's a strong convergence. So if you work with measures, then the goal is always to show that your measure is finally Dirac somewhere, and then you can say, I don't have a measure valued solution to my problem, but I have real function value solution, because then I can say there is a function. So this is always good to have. This is always good to have. So it's a notion that is still many people are not super familiar with, and so the best thing what you can do is to use it in your proof and go back to get these measures. Just take the result out of it. Because then you can say this is just a tool in the proof, and then the result is like that. And the special situation is the following. So assume that you have a I of u, and this will be the functional h of u, x dx, omega, and h is from, say, Rm to R, and it's convex. Huh? And we want to show that lim inf I of uk is bigger or equal than I of u if k goes to infinity and uk goes weakly star because we are in infinity to u. So this is something what we know already from last week Monday, because this is a convex functional. So now there is a new technology, so we can apply it. So you say, okay, so I take a subsequence which does this lim inf, and I can also take a subsequence of it which generates this some measure. So I describe this as the lim I of uk. This is the lim of the integral h of u k of x dx, omega here. And this I can say that the limit can be written as the integral over omega, integral over Rm. I say h of s, mu x ds, dx. It's just there is no g, so this is very easy. So there is no g function. So I just do this. And I look at this middle piece here. So here we have h of s integrated with respect to a probability measure. And h is convex. So there is this Jensen inequality which tells you that this is always bigger or equal than h at the first moment of the measure. So this is bigger or equal than the integral over omega h at I'm sorry. I mean, I like this notation much more, and this is from Danforth-Schwarz, but people normally don't use it. So I rewrite this. So I write it here like d nu x of s as before. So now I write this as d nu x s. So this is just between here and here, this is just Jensen inequality, and then I do dx. And we know that this is the first moment of the measure, and we know that this is ux. And this is known from what we have done here. So this is h of ux dx. So we have it. So this was a simple proof that if you have a convex functional of this type, so H is convex, then Young measures help you to show star Lowry semi-continuity here very easily without Mazur lemma and so on. So this is the case when you use it for the proof and then you forget it and you say, I have my result and I don't have to state it using the measures. Yeah. So that's a long story and difficult story, but because we have like less than 10 minutes, I just tell you how to solve at least some of the problems I mentioned, like this P grows, and then we want to test with a function which exactly has the growth in the space where we have the a priori bound. So this can be solved. There is something which is called decomposition lemma. There are many people, so I think it was Christensen, Fonseca, Miller, Pedregal. And you can also find it in the paper by Acerbi and Fusco about V-Clover semi-continuity from 80s, but it's not, you have to kind of find it there. It's not stated as a result, but you, from the, what they are doing there, you can already infer this. Acerbi, Fusco. So it says like, if UK is a subset of the Sobolev PW1P P is bigger than 1, then there exist two sequences, and this will be ZK and WK, little WK. Both are again here. Such that I can write UK equals ZK plus WK, and there is a subsequence of UK, which I do not relabel again, such that this ZK to the power P is equi-integrable, and the measure the dimensional of the set that ZK is not UK or gradient of ZK is not gradient of UK goes to 0, okay, going to infinity. In particular, ZK generates the same Young measure. Sorry, ZK, but also I'm more interested in gradients of ZK. Gradient of ZK generates the same Young measure as gradient of UK. So somehow it tells you that if you have a sequence which is maybe minimizing sequence for your problem W of the gradient, then maybe your sequence is bad, but you can replace it by a better sequence, and this will be, there is a gradient missing, so that such that the gradient of zk is equi-integrable if you put it to the power p, and the measure where uk is not zk and the gradient of zk is not gradient of uk goes to 0. So in particular, this new sequence generates the same Young measure. So you can always assume that your minimizing sequence has a better property, that it has this p in equi-integrability. And this helps you to pass to the limit, because I already told you that we cannot use the p power as a test function or a function which has a growth like p. But in special cases, when the sequence is better, we can do that. And this helps us to get a better sequence. So this is the one message which is positive. And the second message is that there is a characterization of Young measures generated by gradients. But the characterization is sort of if and only if, but again, it includes some quasi-convex functions. So we don't know, I mean, this is like a characterization which is again very implicit. So if you get a measure, it's difficult to say whether this is a gradient measure, which is called gradient Young measures because they are generated by gradients, or not. We know something, like if you have two matrices, Young measure sitting on two matrices, then we know that the difference of those two matrices has to be rank 1, pointwise, to be a gradient Young measure, simply because this comes from this construction which I showed you, that if you have a continuous function, say piecewise affine, then the difference has to be rank 1. But in general, it's very difficult. So somehow the problem is difficult with quasi-convexification. Now you rewrite it in a different setting, but because the difficulty is in the core of the problem, then it appears somewhere. It's like if you try to close a suitcase which is full of your stuff, and then you sit on one side and then the other side open. So, you know, the problem is not a minor problem, it's really the core of the problem. So many questions are open and they are waiting for new people, new ideas. And so it's a wonderful topic and many open problems. So you're invited to join and work, and you have Ulissa Stefanelli and many other people working in this area, so you can talk to them. And so thank you very much.